Hello and welcome to Boxer's Shorts. I'm Adam Boxer and I'm a science teacher trying to help you understand more of GCSE science. In these short videos I will try and take difficult concepts from GCSE science, break them down, help you understand them, and then do some practice questions on those concepts. In terms of some general tips for using these videos, definitely do not have your phone on or anywhere around you. It's a distraction and it means you won't be able to concentrate properly. The same applies for other tabs on your computer, so don't have your social media tabs open on your computer or laptop, it will just distract you. I'm going to ask you to do some questions. If you don't actually do them, you won't actually learn anything, so make sure when I do ask you to do those questions, you do them. And finally, let me know in the comments if there is a topic that you want me to cover. Thanks for listening, and remember you can subscribe and just let me know if there's something you want me to do for you. First time that our equations start to get a little bit tricky, and it's the first occasion where those of you who have been using the triangle method to solve equations will start to have problems, and why you should be using a technique like Descuse instead. Now let's say I've got a ball and I lift up the ball. Now obviously I've transferred energy to the ball's gravitational energy store, because before it was here, now it was here. Now what we'll do is we'll call that amount of energy EP. Why is it called EP? Energy, and the P stands for potential. Sometimes you'll see it written as GPE, sometimes you'll see it written as E and then GP as little, but the way that your syllabus writes it is like this. What does this depend on? Well, it depends on a few things. The first thing is it depends on the mass of the ball. If the mass of the ball goes up, then the amount of energy I need to lift it goes up. Good luck lifting things if you've not had a good meal. You need energy in order to lift heavy things. The heavier the thing you lift, the more energy is required. What else? The height, how far it goes. If the height is higher, then the energy required is also higher. If I need to lift a mass 1 meter, that's going to require less energy than if I have to lift it 10 meters. It also relies on something else, which we call G. G is the gravitational field strength of wherever this object is. The gravitational field strength is complicated, and again, as I said in the last video, there's some stuff that you're going to be spending more time on later. But essentially, it's the strength with which the object is pulled down. It's the thing you're fighting against. When you lift it up, you're fighting against this thing called gravity that's pulling it down. And we summarize that as G, as the gravitational field strength. Now, if the gravitational field strength is really high, then the energy required is also high. So let's say I took this ball to the moon. On the moon, the gravity is quite low, so it would require less energy for me to lift it. If I took it to Jupiter, the gravity is crazy high. So if I wanted to lift it, I'd need much more energy. What units do we use for these? The unit for mass, we use kilograms. The unit for height, we use as meters. And the unit for G is this thing, newtons per kilogram. What does newtons per kilogram mean? It means how much force is being applied to every kilogram. I'll explain that. Let's say I've got an object on Earth that has a mass of 5 kilograms. Sorry. The gravitational field strength of Earth is 9.8 newtons per kilogram. And what that means is that on every kilogram here, there are 9.8 newtons of force pulling it down. So if I were to split this up, with each section representing 1 kilogram, there's 9.8 pulling there, There's 9.8 newtons pulling there, Same applies here, same applies here, same applies here. That's what that number means. On the moon, that's on Earth. On the moon, G is 1.6-ish newtons per kilogram, which means for every kilogram here, I'm only pulling with 1.6 newtons. Now obviously in this case, that means that I'm going to have a harder job lifting it up, because I've got 9.8 newtons applied to every kilogram. Whereas if it's on the moon, I've only got 1.6 newtons applied to every kilogram. It's going to require a lot less energy from me in order to lift it up. And like I said, you'll learn more about that later on. All you need at the moment is a kind of simple, basic understanding. So our gravitational potential energy equation is the mass times the gravitational field strength. Oh, sorry, I spelled that wrong. Do that again for you. Strength times the height. And what that means is that if any one of these goes up, gravitational potential energy also goes up. So if mass increases, that increases. If G, gravitational field strength, increases, that increases. If height increases, that increases. If any of these increase, you need more energy in order to lift the object. As an equation, we write that as EP equals m times G times H, all in lowercase. Units, joule, kilograms, newtons per kilogram, and meter. I'll write that clearer for you. That's newtons per kilogram. Now, if you hang around at the end of this video, I'll show you that this is just a variation on the work done equation, but I'm not going to go into that now. Let's do some simple examples. Let's say I've got a box or a ball on Earth, has a mass of 2.6 kilogram. I lift it by height of 15.3 meters. And remember, we're on Earth, where G equals 9.8 newtons per kilogram. You will always be provided with this in the exam. It's time for desk use. D, E, S, C, U. Data, I've got mass equals 2.6 kilograms. I've got G equals 9.8 newtons per kilogram, and I've got H equals 15.3 meters. What's my equation? EP equals M times G times H, which in this case is pretty easy to solve. To substitute, I just do 2.6 times 9.8 times by 15.3. I calculate that using my calculator. 2.6 times 9.8 times 15.3, and that gives me 389.844, and my unit there 389.844 joules. Done. Fairly straightforward. I'm going to do another one, and I'm going to write the picture on this side, because then it's easier for me to write the rest of it here. So let's say I've got another ball. This ball we'll say is 3.1 kilogram. It's still on Earth, and I lift it up. I'm not sure how high I've lifted it up, but I know that I've had to transfer 64.7 joules, and I know that I'm on Earth, so I've got 9.8 newtons per kilogram. I tell you what, actually, let's move planets, well, not even planets. We'll move away from our planet and onto the moon, where G is 1.6 newtons per kilogram. All right, how do we solve this? D, E, S, C, U. Data, energy, don't know. M, sorry, no, energy I do know, sorry, I apologize. Energy is written right there, which is 64.7 joules. M equals 3.1 kilograms. G equals 1.6 newtons per kilogram. H is unknown. What's my equation? EP equals M times G times H. 64.7 equals 3.1 times 1.6 times H. I'm now ready for my calculate step. And the first thing that I'm going to do is I'm just going to calculate these two together. So I'm going to get 64.7 equals, get my calculator, 3.1 times by 1.6 equals 4.96 H. Oh, hey, hello. That looks really, really easy to solve and really familiar. We've done something like this before. Just now divide both sides by 4.96. And I get 13.04 equals H. 13.04 meters equals H. It's dead easy. All you're doing is you're just calculating. It's just maths, right? It's just taking two numbers that are next to each other and timesing them together. It's not particularly complicated. It's fairly straightforward to solve. And then that makes, because you've done that step, it makes your rearrangement incredibly easy. On gravitational potential energy, or EP. As ever, have a go at the questions while pausing the video, and then when you're ready, press play again. Alright, so our answers. The first one, if you double the height of an object, you double GPE, because if it's mass and gravity times height, if you double height, then you have to double everything else. How much energy is stored there? Straight calculation. Another straight calculation. Sorry, actually, it's not quite a straight calculation because there is a unit conversion where you have to change 1.2 kilometers into 1,200 meters. Next up, we've got an astronaut lifting a golf ball. So here we change the gravity. So here we're on the moon, so the gravity is a lot less. We've also used a mass in grams, so that needs to be converted to kilograms. Next up, we have an airplane. We've got its mass, 3,500 kilograms. It's a bit light for an airplane, I would suggest, but it doesn't really matter at this point. There's the amount of energy that it stores. So for that, you'd have to do again, that's just a straight calculation. This one asks you for a rearrangement. So you've got a toy helicopter. So it's quite heavy for a toy helicopter. It's about the size of a small suitcase. But again, doesn't really matter for the question. Again, there's a unit conversion there of kilojoules that will need to be changed into joules. In this one, we've got Jupiter, which has a stonkingly large gravitational field. That's because it's so big, it's got so much mass that it just pulls everything in towards it with so much more force. And again, there you'd have to do a rearrangement to get 0.3 kilometers. The question does say to give your answer in kilometers, so that would have come out as 300 meters or thereabouts. So you'd have to change that to 0.3 kilometers in order to get that correct. Okay, well done if you got all those right. If you didn't, have another go. And as ever, please do subscribe and let me know if there's anything that you want me to cover or you have any feedback on the videos. All right, now as I promised you, I wanted to show you that this equation is really just the same as the work done equation. Essentially, the way we do this is by, it's sometimes called consolidating units, where if I turn this into an equation of its units and I had joules equals kilograms times newtons per kilogram times meter, which is just the units for each of those. Now I've got a kilogram times something over a kilogram, which means that these two cancel, which means that joules equals newtons times meters, which is work equals force times distance. Isn't that cool? Now, in fact, all the other equations are related in this way. Those are the equations that we're going to do next. I'm not going to do each one showing you like this how they all relate to each other, because sometimes there's a bit of maths involved that I'd rather not go into on a short video. But in principle, this is why I showed you this equation to start with, because in fact all the other equations are kind of centrally related to it.